So, welcome everyone to the last session of this conference organized in the honor of Professor Ramakrishnan. Okay, and our first speaker of the session is Professor Skoruppa, and the title of his talk is oh, sorry, I forgot to say he is from the University of Siegen. The title of his talk is Mcdonald Identities and Jacobi Forms. If I'm correct.
Yeah, okay, thank you for the introduction. And then I try to give my talk. So I hope that you can understand me and that there will be no problem. Otherwise, you have to interrupt me and say something. Okay, so that's my first slide, as you see. So it repeats the title. It says to what occasion it is, and it shows a big cake for Ramki, of course, with 60 candles. They say I didn't count, of course. Okay, so let me start with the talk. So, as announced, I just want to talk about the Mcdonald identities. And first of all, maybe before I just go on, I just explain what the Mcdonald identities are. I recall it. Many people of you will know. So it involves Lie algebra theory, and but not so much. So I don't really explain about root systems and Lie algebras and the like. But you don't really know need to know it, I guess. So here's the Mcdonald's identities. So the big identities that you see there, first of all, you have to go over it. There's a lot of notations involved, of course. But the first thing is it's a purely formal identity. So it's an identity in the ring of formal power series. So let me see whether I can just describe it. So what you see here is, first of all, something like you have a root system here. And associated to the root system, you can associate a lattice. That's a lattice generated by the so-called co-roots that you find here, the definition, and multiplied or rescaled by the number h, which is which is given here. And so it's a lattice that you have here. And this formal power series identity, there see something like the e to the r, where r runs in the root system or in the lattice. So that is an element actually of the group ring of the lattice. So you take the group ring C and then this square bracket M, right? So all the maps from M to C, which are finite at almost all places. So that is this thing, this ring. And then over this ring, you take the ring of formal power series in the indeterminate X. So that's a formal identity in this ring of power series in the sense of Bourbaki or wherever you find this stuff. Okay, the other notations, as I said, you have a root system here. Then you need also to know what the W is. Okay, W, I didn't explain it. So that's this half sum, I explained it. It's the half sum of positive roots, or the so-called while vector, as people call it also sometimes. There you have this Coxeter number H. Sometimes it's Coxeter number, sometimes it's different. So the right definition is exactly this one here. So it's not so important, these details, but I just give it for the moment. Then you have the while group, W of R. Here, a finite group, and it's a finite sum that you have here. Here you have the character, linear character of the while group. It's actually the determinant of G. And then you have again these elements of the group ring of the lattice M. Okay, so it's this formal identity. And this Mcdonald identity was, well, at the time when it was published, was quite a surprise for people because it did a lot of things. So what it did afterwards was that it somehow triggered the development of Kac-Moody algebras, infinite Lie algebras, and that led in the end also to the algebraic theory of, or the algebraic representation of string theory in physics, for instance, vertex operator algebras, the work on Borcherds on these things, and so on. So it's a very beginning in the 60s that Mcdonald published these identities, and the proof of these identities, it's quite long. It's an Inventiones paper, if I remember correctly, and it's a quite long paper. And the proof is quite long, but in this paper, it's not only the identities that he proved, but actually he develops a theory of affine Lie algebras, and that's maybe the even more important things that he did there, which led into the Kac-Moody algebras. Okay, so these are the Mcdonald identities, and in this talk, I shall present you a very short proof. The advantages of this, or why is it interesting? There are at least two advantages. One is it's short, so you don't have to read the long paper of Macdonald's, though it's of course very important because of these affine Lie algebras that he developed there, this theory. But it's a short proof, self-contained short proof. And the other thing why it's important is that it raises some questions where there are other identities like these Mcdonald identities that one can find. So it just opens the door to some sort of extension of this theory or generalization in a complete different direction. So not in the direction of Lie algebras, but in a complete different direction. Okay, so let me dwell still a bit in these identities. So if you set these e to the r that you see there, these elements of the group rank of the lattice M, if you set this equal to 1 and x equal to e to the 2 pi I tau, as we do always in modular form theory, tau in the upper half plane, then you get this identity for the powers of the eta function that you see here, which some people mess up sometimes. I did for a long time with the Mcdonald identity. So sometimes also these are called the Mcdonald identities. So strictly speaking, they are a specialization only, and you don't get the other one from it. Okay, so these identities are also very nice, at least for modular forms people, if you look at it, because it gives closed formulas for the Fourier coefficients of the powers of the eta function, which is quite interesting. What you also can do, if you look at the denominator of the Macdonald's identities, maybe I can go back. I can. So you see that there is this denominator that you have here. So when you put this denominator to the other side, so that you don't have a denominator, but here's then this vector in front. And if you just replace them, this denominator that you saw there, by the right-hand side of this identity, which is called the Weyl-denominator formula, then you get an identity which, if you take x equal to 0, is just the Weyl-denominator formula. And that's how Macdonald already puts in this paper in the very beginning. His identities can be viewed, as he says, then as a generalization of this Weyl-denominator formula. And indeed, sometimes these Macdonald's identities are called nowadays also the Katz Weyl-denominator formula, because there's also an interpretation, like for the Weyl-denominator formula, proof from Katz-Moody algebra theory and representations of those things. Okay, so another thing that you can do, if you take the simplest root system that you can imagine, A1, then you get a specialization. This identity that I put here below, and this here is nothing else but in a strangely written form than the Jacobi triple product identities. Everybody knows from number theory. So the Jacobi triple product identity is the simplest Macdonald identity, and you can use them, the Macdonald identities, also as generalizations of these Jacobi triple product identity. Okay, so the Jacobi triple product identity usually is, at least for modular forms people or people working in Jacobi forms, represented in the forms that I put here. So I just use the so-called Jacobi theta function, theta tau z, that you see here, the definition of the Jacobi theta function. And then we have this identity that this here has a product expansion like so. So that's the Jacobi triple product identity. And it's exactly what you get when you replace in the Macdonald's identities for A1 that I showed on the slide before. Maybe I can go back to here. If you set x to the e to the 2 pi I tau and e to the alpha to e to the 2 pi I z, right? So then you just get this identity that you have here. And eta is, of course, the dedicated eta function. Well, we had it already. Now, when you look at the Jacobi triple product identities, then of course you can say, well, I don't need the Macdonald's identity to prove it. There are a lot of proofs that one can give for it. And one proof, for instance, the simplest one is that one looks at the left-hand side here, the Jacobi theta function, and one realizes that the Jacobi theta function has exactly 1, 0, so has exactly zeros in the lattice z plus tau z for a fixed tau. So as a function of z for fixed tau, the zeros are just in the lattice z plus z tau. So this this lattice. And so the simplest function which has zeros in this lattice is, of course, the right-hand side, if you look at this. And so it's almost plausible now that you should have an identity with a certain factor coming here. Well, if you look at the expansion here more closely, then you find out that theta tau z is nothing else but the third power of the eta function times the Weierstrass sigma function. So that means you have here the factor eta of tau to put. Okay, so that's a proof of the Jacobi, or a sketch of a proof of the Jacobi triple product identity using theory of, I don't know, function theory, elementary function theory. And so the idea is whether one cannot give a proof of the general Macdonald's identity also in terms of function theory. So what you find here, actually, if you just look at this more closely, we know nowadays call this a Jacobi form. And so the first question is, of course, when we just specialize these variables x and e to the r, these formal variables in the Macdonald identities, whether we should not get them also Jacobi form. And that turns out to be true, of course. And from that, we shall see them, how we can get these identities in a quite nice short form. Okay, so that is the question, so to speak, the leading question or guiding question in this talk. So whether we can give a proof for these Macdonald identities along these lines. Function theory, Jacobi form theory, we'll see. And it works. Okay, so the observations are, as I indicate already, that first of all, indeed, the formal power series that you see in the Macdonald identity, you have a formal power series on X, and then you have this product expansion on the right-hand side, on the left-hand side. So this formal power series in the Macdonald identities is indeed a Jacobi form, but the Jacobi form of lattice index. So extension of the notion of Jacobi forms as just given by Eichler and Siegen 40 years ago. And these Jacobi forms that you have there in the Macdonald identities, they are of singular weight. I explain later what this means, but singular weight Jacobi forms are quite rare. They are somehow something that one always should look very interested at, because usually they are connected to very interesting things in mathematics. So they are not just only Jacobi form things, they are quite rare and interesting. In a different way, as you will see also in this talk, they are essentially invariants of so-called Weyl representations. And the as I indicate already, the theory of the Jacobi form lattice index that I will sketch here in a moment provides a very simple explanation for the product expansion in these Macdonald identities. And it's even easier than the proofs I sketched for the Jacobi theta function. We don't have to count zeros or things like that. It's just a miracle. It works. It just works essentially by the miracle of modular forms, as Zaghi called it. Sometimes that the space of modular forms are of higher dimension, a very simple thing, but we use it very often in arguments. That it's sort of miracle which gives us a lot of results, and it's essentially something that works here also. By the way, I mentioned the name Zaghi. So parts of the results that I explain, I just didn't put it always carefully, grew out of a joint paper with Gritsenko and Zaghi on so-called theta blocks. And so there's a preprint and maybe also soon some official publication of the theta blocks. You find that in archive, if you like, since 2 years, I think. And there you find also a lot of things that I explain here. Actually, you'll find this proof here also in this paper that I give here. Okay, so the plan of the talk is so that I want to describe precisely the Jacobi of lattice index. So that will be a bit boring for some people who know it already. For others, it will be a bit too fast. It's always a bit unlucky with the Jacobi forms. There are a lot of notations involved, but I have to do it so to get to the points here. And then I show that these product expansions that you see also in the Macdonald identities, that they just happen by so-called pullbacks of Jacobi forms of very simple type. So that's also a sort of miracle in this theory of Jacobi forms, that you can almost all important Jacobi forms that I know you get as pullback of a very simple Jacobi form. It's also a sort of miracle, but it's true. So then I just give or sketch the Jacobi forms proof of the Macdonald identities. And as I said, there are some natural questions that evolve during the proof and that one would like to discuss, and none of it is solved. And maybe if there's some time, I give some applications to explicit number theory. So it has to do with elliptic curves. And if you have an elliptic curve, you have the over Q, you have the associated modular form, and you have the associated Jacobi form. And the Jacobi form is interesting because the Fourier coefficients essentially give you the value of the L function of the elliptic curve that I started with at the critical point. And these Jacobi forms, one would like to have explicit formulas for it, like in, for instance, tunnel theorem. And this theory here gives puzzling simple identities for Jacobi forms of many elliptic curves, so that maybe I go into it. I don't know whether the time suffices. Okay, so let me start with Jacobi forms of lattice index. That is the part that we go into now. And so the first thing that we need, unfortunately, it's a bit technical, is the unique non-trivial central extension of order 2 of SL to Z, which I call MP to Z and called sometimes metaplectic cover. So some people just complain about this sometimes when people do it. And so it's, as I said, it's just the central extension of SL to Z. It's a twofold extension. So it's central, as you see here, that's the center of MP to Z. And it's non-trivial to characterize it because there are only two, up to isomorphism, only two extensions of twofold extensions, central extensions of SO2Z, and that's a non-trivial one. So Shimura gave long ago a nice description, explicit description of it, just as pairs of matrices and then roots of this C tau plus D, where CD is a usual thing in the matrix A. You have two square roots, so that is a double, twofold extension that you see here. So for every A, you have two values. And then you have the usual multiplication that we know from model form theory. I mean, model forms of half-triangle weight. So Ramke and Manikam and other people worked lifelong on these things. So that should be to the audience quite well known. One notation I need here, namely, I just need a linear character of this group MP2Z. So homomorphism to C star. And that is the following. I take the Dedekind eta function at A tau and divide by W tau. So AW, W is the square root that you see here, times eta of tau. So we know that this is a 24th root of unity here, and it's of course a character of MP2Z, a linear character in homomorphism into the group of unities of order 24. And actually, this one generates the group of characters of MP2Z because there are only 24 characters, and it's cyclic, this group of unit characters. Okay, so that is one thing that we need. So Jacobi forms, space of Jacobi forms come with three parameters. So one is a weight, which is some integer or half integer. For the half integers, I needed here to introduce this group MP2Z, but we have to consider here Jacobi forms of half-triangle weights. They're very important in this theory. The other things that we have there is the character, because Jacobi forms are somehow modular under the group SO2Z, but actually it's MP2Z because of this half integer weight, possible half integer weight. So we need the characters, there are 24, and the group of characters are generated by this epsilon. And we need the index, and the index for the general theory, it's a lattice. So it's not a number, but a lattice. And so I have to explain shortly some notations of lattices to fix notations, and maybe also something that not all people know. So when I say lattice, it's always a symmetric positive definite lattice. Symmetric anyway, positive definite lattice. So more precisely, it's a pair L beta, and L is a free Z module of finite rank that I didn't put. And beta is a symmetric positive definite Z bilinear map, so it takes values in Z. I don't say 2Z, so it's not necessarily even the lattice, but it's integral. So the values are always of this form beta are always in Z. So usually I set beta of x equal to 1/2 of beta XX. So it's just a convenient notation, and I use it very often, so I put it here very explicitly. So you know that we call it lattice even if beta x, so that means beta XX is in 2Z is even, so that means if beta x is integral, right? And otherwise we call the lattice odd, so then beta x takes values in 1/2 Z, and really in 1/2 Z. And then we can consider the map x to beta x mod Z. And okay, so if beta x is integral mod Z, that is a trivial character, but otherwise it defines linear character so that one can easily check it's a linear character indeed into 1/2 Z mod Z, so of order 2. That also is quite important for us. And then, and then there is another notion. When we have a lattice, an even lattice, we usually, well, any lattice, we talk of the dual lattice. But that doesn't suffice for us here. So if you have an odd lattice, the dual lattice doesn't suffice. We need something else, which is called sometimes the shadow of the lattice by I think, Conway Sloan introduced it in the 90s, this notation, or this language. So, so what is a shadow? So you take the lattice L, and then you tensor it with Q, of course, so that you get a Q vector space, and then look at all S, so that beta Sx is, so if beta Sx would be for all x in the lattice, always an integer, so if this would be congruent 0 mod Z, right, then we have the dual lattice. But that's not what we want here in this case. We take the lattice L star, which is, of course, if beta x is always an integer, it's nothing else but a dual lattice. But if L is an odd lattice, then of course it's different. And it's this definition that I give here, and this definition just makes it that it's not just L star, right? L sharp, it's a dual lattice. So if L is even, this L dot equals L sharp. Otherwise, it's slightly different. One can work out more precisely what it is, but I don't want to go into it. So then we have the maximal even sublattice of L. So that is, of course, nothing else but the kernel of this map x to beta x mod z, the maximal even sublattice. Okay, so that is what we need for lattices. So the shadow is quite important for us also. I'm sorry for these technical things, but it's just like that. So now finally I come to Jacobi's form lattice index. So as I said, we have 3 parameters for each space. So here we have the weight, which is integral or half integral. We have the lattice L from the side before, from the page before, from slide before. And we have a character of MP to Z. So some power of epsilon then, of course, and this H can be viewed as an integer mod 24, since there are only 24 characters. Okay, so then what is it? It's a space of holomorphic functions in 2 variables. One is in the upper half plane, as we know for Jacobi forms, and the other one is in tensor that is L with C. So if L has rank n, so that's an n-dimensional C vector space, so isomorphic to C to the n, if you like, and Z runs in this C to the n then. And we look at these functions, and then we have these usual transformation laws for Jacobi forms. I put it here, but we don't have really to read it now very carefully. It's just this modular property that we have, right, with respect to the group MP to Z in this case, to make it precise. If you have half integral rate, and you see here coming in the character in this transformation formula, and then some factors that one knows from the theory of Jacobi forms. And we know that this function is quasi-periodic with respect to L plus tau L. So that means we have some quasi-periodicity here. But there are, again, some factors showing up that one also can discuss, but I don't want to discuss them here. We don't really have to discuss them, but they are there. Okay, and the third condition is that phi is holomorphic infinity. And what does this mean? Well, that means the following. So if we take a function, as I just put it here, which satisfies these conditions 1 and 2, so this modular property and this quasi-periodicity, then this function has a Fourier expansion, of course. And I put here, ignore this red thing. It has a Fourier expansion of this kind. So some Fourier coefficients and this e to the 2 pi I tau n, and then this e beta rz. So that is what we anyway have. And indeed, this r runs here in this L dot, the shadow of L. In general, if L is an odd lattice, otherwise, of course, it's a dual lattice. And what we want is that the function phi is holomorphic infinity, and that means that here in this Fourier expansion, we have that these Fourier coefficients vanish unless n is greater or equal to beta of r. So that is, of course, something which in general would not be fulfilled if you take a function which satisfies only these transformation laws. But we impose this also as a condition. It's a very natural condition in a sense, but also, again, I cannot discuss it here. Okay, so that is what we understand by a Jacobi form of lattice index. And then there is something that I need here, namely the theta expansion. So say for the moment that that the lattice L would be even. So then this L dot here is just a dual lattice. And then I have here L dual mod the lattice L. L if is then of course L if it's even. So L sharp mod L. So it's a finite group that you have here. So a finite set, and we have this group even. And we have then consider then a map lambda on this finite set to C. And then we can put with this function lambda r what I put here. So a theta function, q to the beta r runs in L sharp, so the dual lattice, e to the beta rz. So that's obviously something which one calls theta function. And that's it. So if we have an odd lattice, then again, it becomes a bit more complicated. So this lambda is then some map, again, an L dot mod L eve, which satisfies a certain condition here, which comes from this factor that we saw in the transformation form of these Jacobi forms. And again, we define a function here. And the main point is that how many functions are there? So the dimension of the space of such functions is just the dimension of L sharp mod L for even and odd lattice, always. So that means when I just look at these basic theta function that I put here for all lambda is above, so the space spanned by it, then this space here that I denoted theta of L is just an, say, n-dimensional space if n is the number of points in L sharp mod L. Okay, so it's a finite dimensional space. And it's known since eternities that MP2Z acts on the theta L. Well, for the shadow, it's maybe not so known, but it's also not difficult to work out. So it acts on the theta L. The action is, of course, the action, here's this slash action n half that you saw there in the transformation formula of the Jacobi forms. And if one studies with this action, one has then a very natural isomorphism between the space of Jacobi forms and the spaces that you see on the right. So on the right here, you see this MP2Z module, theta of L. You see the MP2Z module of modular forms on the group gamma of L, where L is the so-called level of the lattice L. Modular forms of weight k minus n over 2, and also the group MP2Z acts on it, of course, from the left by just slashing it with g to the minus 1 as I did here. And so it's left action. And you see here the one-dimensional MP2Z module, which affords the character epsilon to the h. And the tensor product of this is then also an MP2Z module. And you look at the MP2Z invariance of this one here. And this is nothing else but the space of Jacobi forms. It's a natural isomorphism that you have here, which I just described. I don't describe now, but it's a natural isomorphism that one can very easily deduce from the definitions, this isomorphism. And it gives us immediately then certain results. One is that the space for arbitrary lattice is always finite dimensional. Another one is that we don't have any Jacobi forms if the weight k is less than n over 2. N is the rank of the lattice, so n is always the rank of the lattice. And this n over 2, this weight n over 2, where we possibly have Jacobi forms, sometimes not, sometimes we have. It's a quite interesting question when we have and when not. That is, of course, then this space here. It's just this theta of L, this finite MP2Z module, tensored with this one-dimensional Z module, and the invariance of it. So this here is a so-called Weyl representation that you have here. And so the space of Jacobi forms of weight n over 2, and again, the rank of the lattice, is nothing else but the space of invariance of this Weyl representation that you have here. So it's just actually has nothing to do with Jacobi forms. It's just purely an algebraic object. So a representation of MP2Z, a finite dimensional representation, and the invariance. Okay, so this weight n over 2, it's called singular weight. It's for us a very interesting weight, as we will see. Okay, so that is what I have to explain here. So when you take a special lattice, the lattice which is L, and then this scalar product, the usual one, just multiplication xy, and then rescaled by 2m, where m is an integer. Then the space of Jacobi associated to this lattice with trivial character and say integral weight is nothing else but the classical Jacobi forms that you know from the theory of Eichler and Zagier. So this theta tau z that you saw the Jacobi theta functions, z is then a Jacobi form now in this notation of weight 1/2, index 1/2 in this sense here. So that means belonging to the lattice z itself. So where 2m is equal to 1. And the character is epsilon cubed. So one can work it out like that. A very important function for us is a very simple one, but it's really important. So I take the standard lattice z to the n. So z to the n is the usual scalar products that we all consider in the first year of studies of mathematics, or in high school, I don't know. And with this, for this lattice, I can construct immediately a modular form of singular weight for this lattice by just taking the variable, writing z as z1 up to zn, and just taking this Jacobi theta function that you see here and just insert z1, z2, zn, and it's easily checked that this is indeed then a Jacobi form, singular weight in this case, for the lattice z to the n. And the character, of course, is then something like epsilon to the 3n, something like that. So I put it here. So that is a very simple Jacobi form. Still, it's quite nice because, of course, it's a 3n tuple product that you see here. So it has quite nice description. Anyway, so it's quite simple. You might think, nah, yes, it's a trivial example. However, there is some simple effective construction method for Jacobi forms, and that works as follows. And we can then just apply it to this very simple Jacobi form that I gave for the standard lattice z to the n. And that works as follows. So if you have two lattices, say L and L prime, and you have an isometric embedding. of the lattice L into L prime. Then you can consider the pullback in the Z variable of Jacobi forms from the lattice L prime to the lattice L. So this defined like this, right? You take a Jacobi form phi in this for the lattice index L prime, and then you apply this alpha star by just taking phi tau of alpha Z, right? And that becomes a Jacobi form then, as one checks quite easily, for the lattice L. So that gives a map from Jacobi forms from L prime to L. So a contravariant thing that we have here. And in particular, I can apply this if I have an embedding from L into Z to the N, so the standard lattice, L into Z to the N, then I can apply this construction to the Jacobi forms that we saw here, this very simple one, right? So this product of the Jacobi theta functions, where we just vary the variable here according to the coordinates that we have in the Z vector. And if I do this, then I get just here the theta tau alpha 1 up to alpha nz, where these are the components of our embedding alpha into Z to the N, right? And that's in the Jacobi form, indeed, of single weight n over 2 for the lattice L now that we embedded, right? And the characters in epsilon to the 3n. So it's a Jacobi form. And what we can still do, let me see now, that comes in a moment, is that maybe we just say, well, yeah, but the lattice L is, compared to n, has quite small rank. So that is then a Jacobi form here of quite big rank n over 2 for the lattice L that we have, right? So L might be a one-dimensional lattice, for instance, and n might be 1000. And then we would have a Jacobi form here of weight 500, but we want a Jacobi form maybe of weight 3 or 4. What we can do is we can just try to divide this here by a power of eta. If we do it correctly, then this condition for holomorphic infinity is still fulfilled, and we get a Jacobi form. And the point is that, as I indicate already, every Jacobi form that is really interesting that I know is obtained exactly in this way. So that means you start with this very simple Jacobi form for some standard lattice Z to the N, Jacobi theta function. Then you take an embedding of your lattice L into Z to the N. You make this pullback, and you divide maybe by some power of eta. You have to discuss it in a moment when you can do it, when not. And you just get a Jacobi form, maybe of much smaller weight. And this Jacobi form, if you don't know its provenience as pullback of something, might be a very complicated Jacobi form, right? It looks complicated, but indeed, all Jacobi forms, which are very complicated, which occur in the theory of elliptic forms or whatever that you find in all kind of books or so, they just can be obtained like this. Of course, there will be some that cannot be obtained like this, but they might be not so interesting. Anyway, so it's a very, very interesting, simple construction which leads to all kind of non-trivial results that we know in the theory of Jacobi forms. So pullback and this standard theta function associated to the Z to the N. So there are two questions, of course, if you believe me that this is really this simple construction leads to a lot of interesting identities. The first question is, yeah, well, given lattice L, when can we embed it into Z to the N for some N? Is it possible, always possible? How many embeddings and so on? And the other thing is, can we divide this, or by what power of eta, of the eta function, can we divide it so that we still get a holomorphic, a Jacobi form with holomorphic at infinity? So let me see. So the first thing is, so if I, so the number of embeddings from L into Z to the N for varying N, right? It's finite. So there are only finite many embeddings anyway. Of course, you can just take an embedding and then you just put make an embedding into some larger Z to the N plus 1000 by just adding 0 components, 0 components to alpha. So if I exclude some trivial nonsense like this, then of course there are only finitely many embeddings, and that's quite easy to see, because if you write the quadratic form as a really this is better as a quadratic form by choosing a basis for the letters, then these alpha jz also becomes in linear forms in Zj with integral coefficients. And what you're asking for is to write the quadratic form associated to beta of x as a sum of linear polynomials, linear homogeneous polynomials with squares of linear homogeneous polynomials with integral coefficients. And of course, there are only finite many solutions. And that gives immediately also an algorithm, so a very stupid one, for calculating all the embeddings, right? You just write your quadratic form, by linear form beta, or this quadratic form beta of x that you have, as really a quadratic form by choosing a basis, and then you just try to write a sum of linear polynomials, squares of linear polynomials with integer coefficient that one can put on the computer, but it works, of course, only for small ranks. So for the lead lattice, of course, you would have a hard time already to compute all the embeddings. Another question is, which lattices permit embeddings into Z to the n? Conway Sloan studied this question long ago in the 90s, I think, and they called such lattices integrable lattices for some reason. And they proved in one paper that they had all lattices of rank 5 can be obtained by such embeddings. So that means if you have lattices of rank less or equal to 5 and you want to construct Jacobi forms, go ahead, you always can do the constructions that I said and you find non-trivial Jacobi forms. So the first, sorry, that I did something, okay. So the first lattice which is not integrable, so which has no embedding into any Z to the n, that is E6, lattice E6. It's quite easy to prove, you find it in one of these papers of Conway Sloan. And the open question is, of course, as I said, when you have a lattice of high rank, which might be interesting, like the lead lattice, how do you find all the embeddings then, right? So there, the algorithm that I sketched, and I don't know any better one, just fails, right? Just because we cannot wait so long for the computer. Okay, so the other question is, if I have this pullback, I want to divide out by a high power of eta, if possible, to get some Jacobi form of maybe smaller weight, because they're more interesting. And by what power of eta can we divide out? So the question is, so if I take this standard lattice, so theta Z to the n that we saw there, have the embedding of that is L into Z to the n. And if I take the pullback and divide by eta to the L, then this is not necessarily holomorphic at infinity, but the condition is it's holomorphic at infinity if and only if, and here's a condition, if this sum that you see here, so this fine sum, with a certain function b, alpha jx, the components of this one, right? If this is always for all x in R tensor the lattice, so this R vector space generalized lattice, greater or equal to L over 24. So this L that you see here, right? L over 24. So that one has to work out. It's not very difficult to prove this, but it's an essential point. I call this here B alpha x, this sum that we have here. And the bx that you see here, that is this function here. So it's essentially, it's somehow like the second Bernoulli polynomial, well, up to some additional factor, added factor, and then cut between 0 and 1, and then continued periodically, that we consider very often in number theory. So here's the definition that I gave here. So this is function beta of x. So this function beta alpha, if you have embedding, that's then a function that I put here one example, which is piecewise differentiable, of course, piecewise quadratic. It's periodic, right? And it just might look like this, right? And the point is, when we just want to apply the criterion that I put here, then we have obviously to calculate the minimum of this function for all x in the lattice in the R vector space generated by the lattice, or in some fundamental mesh, because it's periodic, this function with respect to the lattice. So, and the question is there any effective way to compute the minimum? Of course, one can compute the minimum. It's not really difficult to work out that the minimum is always taken at some point in the vector space generated as a Q vector space generated by L. So the points are always rational, where the minimum is taken. And you can even give a bound for the denominator of the points where the minimum is taken. And so you can search then by this, right, in a fundamental mesh. But that, again, doesn't work for lattices of, well, it just doesn't work because it just, the computer cannot do it, right, in reasonable time. So that one also would need a better algorithm. So it just doesn't work really. So to get a bit the hand on these things, the embeddings, and also this criterion that I gave here, what one can do is one goes to a more intrinsic description of embeddings of a lattice. And the intrinsic description is the theory of eutactic stars. So it's quite simple. So when you have an embedding and you take this alpha j, then it's easy to see that there must be a Sj in the dual lattice, really dual lattice, not the shadow, in the dual lattice of L, odd or even lattice, doesn't matter, such that this alpha j of x can be written as beta Sjx, right? So it's just by the definition of dual lattice. And so then, since this is an embedding Z to the n, isometric embedding, you have, of course, that beta xs is equal to what I put here, right? So the beta Sjx squared, So this sum. So that means just it's an isometric embedding. Right? And so we look then as families of such elements in the dual lattice, which satisfies this condition. And this condition can be described also then in this way, as an identity for beta xy, or as a sort of pseudo-orthogonal basis, so to speak, for the lattice L that we have, right? So these three conditions that I put here, they're all equivalent. And if you have some family of elements Sj in L sharp, which satisfy one of these identities, then this is what we call a eutactic star in the theory of lattices, right? So that's a eutactic star. And of course, if you have an embedding, you get an eutactic star, and vice versa. If we have a eutactic star, then you get an embedding. So that means we can forget about embeddings, and we only have to talk about eutactic stars. So we just have our lattice, we have L sharp, we look at families which satisfy these identities, and that is some sort of intrinsic description of embeddings that we have. And that helps us to study it a bit more closely. So if we have an eutactic stars, then we can again consider this function, and that is of course nothing else but the pullbacks that are always considered, so that these elements of the family of the eutactic star Sj, I put them here. The beta 1 is nonsense, the 1 has to go, so this beta is 1 of z, beta is n of z. Okay, so that's this pullback function. And of course we want eutactic stars, right? So that this minimum that we saw there, I translate now all these things that we saw to eutactic stars, so that this minimum that you see here is greater or equal to capital N minus small n over 24, right? So something like that we look for, and if we have, for instance, something like that, then we can just get Jacobs of very small weight. So in this case, it would be singular weight. Okay. So that is for the embeddings, but now we have the things that we just want extremely eutactic stars, so that eutactic stars which satisfies this condition here. And again, this, as I said, that is very difficult to handle. This minimum, we don't know if we have a lattice over a eutactic star, what the minimum is. So in general, we have no idea. So there's no formula giving us this. So, but there is a sufficient criterion that some eutactic star is extremal in this sense here, right? Satisfies its identity. And that again looks a bit technical, but it's quite nice criterion. So what we do is we take a subgroup of G and theta of L, which leaves the Sj invariant up to sign, right? So that might happen. So maybe it doesn't happen, but maybe it happens for some eutactic star. And I will give examples in a moment. And if we have something like that, so a subgroup G and OL, which leaves invariant this eutactic star up to sign, so permute the elements of the eutactic star up to sign, then we can set the sign of G in the subgroup G, where we take this epsilon J, so the signs which come in when we permute, right? So if you apply G to an Sj, then this is S sigma J, sigma is the permutation associated with G, right? Times some sign. And that takes the product of these signs, and then one can show that this is indeed defines a linear character of the group G that we have here. Okay, so that's one thing. And the group OL, the orthogonal group of the lattice L, that acts, of course, on theta L by pullback, right? So because every element in L gives an embedding from L into L itself. So actually an isomorphism, isometric isomorphism of L with itself, and so it acts then, of course, on Jacobi forms of lattice index, but also on the theta L. Why is this pullback that I just gave? And this action that I have here of theta L that intertwines with the action of MP2Z. That's very simple to see. So we really get them Jacobi forms. And the other thing is that if I take this function theta S that I can associate to the eutactic star, this pullback of the associated embedding to S, right, and apply some G, right, G star, then I get just, again, the theta S up to sign, and the sign is exactly this character that we see here. So we have always a function theta S which satisfies this identity here. If we have a subgroup G which leaves invariant eutactic star, permutes the elements of the eutactic star up to sign. Okay, so, and we call now the eutactic star G extremal, right? if this space, right, of all thetas in the space of elementary theta functions for the lattice L, if there's only one function, right, which satisfies this identity. So if the space is one-dimensional, then we call it G extremal. And as you will see in a moment, G extremal implies, of course, that we have an extremal eutactic star. But of course, not every eutactic star is G extremal for some group G. But it's sometimes sufficient to look at this G extremal to get something. Okay, so so that's actually an algebraic condition, as I said, because we deal here with representations, and so it's not very difficult to check this. So it's much easier than computing this minimum for a lattice, and you have some theoretic handle here to deal with it. Okay, so here's the theorem, which is a sort of general pattern for Macdonald's type identity. So assume that we have a lattice L, integral lattice of rank n, and we assume that we have a eutactic star, S which is Z extremal for some subgroup G of OL, right? And what do we have then? Well, then we have this identity that I put here, right? So then there is a certain vector in this shadow of L, and there's a constant gamma, so that we have this identity. So you see on the left-hand side, we have this theta of S, so this pullback of the associated embedding, the embedding associated to S, right? And then we divide out by eta to the little n, the rank of the lattice n that we have, and then the capital N, the number of elements in the eutactic star, or the dimension of the Z to the n in which we embed, right? So we have this product divided by this eta power, which is a Jacobi form. Well, we have this, and this is equal to up to a constant to this expression that we have here, right? So the left-hand side is Jacobi form, so that means the right-hand side must also be Jacobi form, and the right-hand side is holomorphic infinity, obviously, when you look at this. So that means we are allowed to divide out by this power of eta. So indeed, we have here a G extremal eutactic star. Sorry, that is a question. We have here some extremal eutactic star, right? Okay, so that means G extremal implies extremal. So the G has to go here. Sorry that I just messed up. Okay, so that is, as you see here, that is very close to the Macdonald's identity. And actually we get the Macdonald's identities from this here. So, but here we have an arbitrary lattice and the G extremal eutactic star, and we have always such an identity, Macdonald's type identity. Now, the proof is very simple, so I just put the proof, but I think I don't give the proof here, so I just put, maybe because I just over time already, but you gave an introduction also. So let me just short it, I don't give the proof here. So the proof is very, very simple. It's just a simple calculation with Jacobi forms, and we need, of course, in this proof, we use that the space of Jacobi forms are finite dimensional. So maybe the slides are available, then you can just look up the proof if you're interested. It's a very simple proof for this theorem. It's not very difficult. You find it also in the joint paper with Zagi and Gritsenko in the archive if you're interested in such details. So let's look at root systems, right, and eutactic stars. And indeed, if we have a root system, say an irreducible root system, and say the ambient European spaces, then we call then R, and that we have here some scalar product with it. We choose a system of positive roots, R plus, then we know that there is an identity. We always say the identity for any reducible root system, this identity that I put here, right? So the XX, so this bilinear form that we have here, is equal to Rx squared, where R runs here in the through the positive roots that we have. And that is an identity which is true for all elements in the ambient Euclidean space that you have here. And here comes some number H coming in. Sometimes it's so-called Cox's number of the root system, but not in general, if it's not a pure root system. So it's just this number that I put here. So sometimes it's a Cox's number, if all roots have the same length, otherwise not. And so we have this identity, and this means this identity, if we just do the right rescaling, so if we just consider all X and E, so that X are H is in Z for all R and R, right? So this here, this is a lattice then. And if you take our scalar product from the Euclidean space and rescale it by this number h here, then this identity can be interpreted as, we have an embedding of this lattice R into z to the some n, right, where n is just this number of positive roots that we have here. And so this R plus that we have here is a eutactic star on this lattice R underscore that I put here. So we have a root system. We can look at this this lattice that we have here, right? Sometimes it's called the co-root lattice that we have here. We rescale the scalar product by this number h, right? So that this identity becomes then an identity saying that the positive roots form a eutactic star, and on this co-root lattice that we have here, R bar, right? Okay, and now we take the while group G of R, and then, sorry, the theorem is that the eutactic star R plus on this co-root lattice R is extremal with respect to the full while group G that we have, right? So that's a theorem which we can apply immediately to this identities that I put, right? So this identity here, so this identity holds in for this root system R, and this identity is then nothing else but the Macdonald identities. So that's the proof for the Macdonald identities. Of course, the proof uses two things, right? One thing is the proof of this theorem, but that's really a very simple thing in the theory of Jacobi forms. Sorry, here I put the proof. I mean, it's sketch of proof, say, but we don't go through it. And the other thing is that, of course, we have to, that we have to prove that indeed this R plus, it's a eutactic star, but we have to prove that this is a G extremal with respect to the while group G, right? And that is also quite simple proof. So it's just simple in the sense it takes not more than half a page or even less, I think. It's also in the preprint if you're interested in that. But it's not really simple. So I needed, I don't know, several months to find the proof. I mean, not every day working, but from time to time coming back to it. And it took me really very long to work with it to find the proof. But it was more maybe due to my ignorance of root system theory and that's like. In the end, I found the proof. It's very short and simple. It's a direct proof. There's nothing fancy in it. I don't cite big theorems or whatever. It's straight from the definitions of root systems that you can derive. That the eutactic star plus, right, that I have here, is just G extremal. So it's really an honest, simple proof of the Mcdonald identities. Okay, so unfortunately, when you specialize, you get the Mcdonald identities, and of course, that's what I said already. So I just stopped the talk here because I just went over time. The interesting thing, of course, is that one might look for extremal eutactic stars different from root systems, right? So that would be interesting to find because that would just give new identities, Macdonald's type identities, but new ones, right? That would be for many, many reasons interesting. It's just interesting for modular forms people because it gives nice identities again for the eta function, whatever. But it's interesting, of course, in a more fancy way for physicists, for instance, right, who look for more interesting vertex operator algebras, not only those who come from these Kac-Moody algebras or affine algebras and so like. Okay, so one can of course make a systematic search for something like that, but it's, as I said, with a computer, but it's quite limited because we cannot compute so much. Okay, so I think I stop my talk here with these few words that I already mean very honestly. So happy 60s Wamki and many, many, many more active years. Thank you.
Yeah. Thank you, Professor Skoruppa, for the talk. Nice talk. And if there are any questions or comments, people can ask now.
Maybe one question from my side. Hi, Niels.
Hi. Yeah.
Also the Macdonald's identities had been somehow the starting point of Borchards. I mean, like denominator formulas and y-denominator formulas. So, is there something possible in in several variables. I mean, several variables in the sense of the individual theta series.
Well, I'm not sure that I understand the question correctly, but I just try and answer. You tell me when the answer is nonsense and not referring to a question. So yeah, so if you would have a different type, so additional Macdonald type identities now for lattices different from the root lattices, that of course is interesting because people would immediately look at it as an interpretation of some denominator formula of some exotic infinite Lie algebra, right? Kac-Moody algebra, something that they didn't have on the table for the moment or so, right? And physicists are very much interested in those things. They just immediately derive from this and again a vertex operator algebra, right, which represents in whatever, and they would just look at it. So in that sense, it's interesting for many people. So that's what also some people like Nam, for instance, told me when I just gave this talk at another occasion. So they would be quite hot about it, right? But I really have no feeling, so to speak, about whether there are really additional lattices or whether it's the root lattices. Maybe it's only the root lattices which are extremal in this sense, have extremely eutactic stars, and no other lattices, right? So if you can prove this, then you have another description of root lattices, which, okay, you can put it in some paper for academic reasons, but that's, of course, not so interesting. But maybe it's the truth. But maybe also that's the other lattices. I really honestly don't know. And I have no direction to say, yeah, I tend more to this answer or that one. I have no idea.
And maybe second question, why has this proof not found earlier?
Well, it's a nice question in the sense that I hope that then maybe the talk was not too technical and you saw that it's indeed quite a simple proof. But of course, to find this proof, that was also not so easy. It took several years actually with several curves, right? So it's the first time when I saw these Mcdonald's. So we worked on theta blocks or so, right? And at some point, Gritsenko and me at the same time, more or less, had the feeling that this should have to do with root systems, and we worked on this. It took almost a year until we discovered something, right? And it was not straightforward. It was just we really had to work through to discover that this has to do with Jacobi forms, right? So I mean, now as I presented it, it looks quite straightforward, just very logical, right? But it was a way to go.
Mm.
It also the way it took me really a long time to prove this little lemma about that this root system associated to the eutactic star associated to an irreducible root system is indeed extremal. So that was not at all trivial or so. That I sat there sometimes. I remember I went to Neil and we sat several afternoons with Gritsenko and could not find the proof. So it was also not straightforward. Now that the proof is there, it's almost, when you look at it, very natural and easy, right? But it took so long. So
okay.
But it's nice that you say simple, because then it's indeed true. So it's really simple.
No, actually, I said not earlier, because it's clear theta blocks and the techniques you use are, at least at the first glance, quite natural. But then, of course, as you mentioned several times, there had been a lot of parts which had been dependent on finding the gap or to solving the gap, as I understood.
Yeah. Actually, that also was somehow the reason to invent Jacobi forms of lattice index. I mean, of course, Jacobi forms with several variables existed before, and people looked into it, but they never looked so concisely into it, so to speak, right? So you need the right notations, as I use here with these lattices, quite abstractly dealing with it to get really to these identities. Otherwise, you don't see it. If you do this in linear algebra form with matrices, whatever, matrix index, whatever, you would never see something like that, right?
Mm. Okay.
So you really have to do these things spaces independent, right? So to find your way through, otherwise you got lost in a lot of identities that you don't understand. So.
Yeah. Okay. If there are no further questions, let us thank the speaker and